Okay, so there's one more algorithm I want to talk about that's less well known than k-means, but it has slightly nicer properties, so it's another good one to be familiar with, and that is Dbscan. So how Dbscan works is, given points, say, in a two-dimensional space, as always, we're going to look for points that are separated by a distance of no more than some epsilon. Okay, and so if you can hop from one point to another by hopping no more than epsilon at each point, then all those points will be considered to be in the same cluster. And so whenever you need to jump a little further than epsilon, you'll be entering a new cluster. Okay. So in this example, if epsilon is this distance, then we know we can get, I think it's driving me nuts a little bit. These points are within epsilon, these points are within epsilon, and so on. And so you sort of induce this graph over the data, and so all of these, A is, B is reachable from A by hops of no more than epsilon, so all these are in the same cluster. And actually, C is also reachable from B by hops in the same cluster, but D is not, and so D is in a different cluster. So all the solid points are in one cluster, and all of these hollow points are in another one. All right. So there's some advantages here that are kind of illustrated by this picture. So one is it can find non-linearly separable clusters. So right here, there's no line you can draw to separate these two clusters, and yet clearly there's kind of a dense region and another dense region. And so you want to try to draw a curved line. And Dbscan finds this naturally, but k-means won't. K-means will sort of find a point, depending on where you start, maybe here and here or something. In which case you'll get clusters like this. Okay. So there is no dependence on a fixed number of starting clusters like k-means was. There's no dependence on starting conditions. You sort of compute this from any of the vertices in the graph and start making hops. There's only two parameters to this. One is this distance threshold epsilon, and the other is a minimum number of neighbors. And what this controls is, like if I find a point way out here in space that doesn't have any neighbors, only has a few neighbors, then maybe I just consider that point noise and I ignore it completely. I don't try to put it into any cluster whatsoever. And so here, if you put min neighbors at 0, you'd get this one in its own very own little cluster, this one in its very own little cluster, and so on. And so that just it requires extra bit of bookkeeping. It's not necessarily a big flaw in the algorithm. You'll still find the obvious two main clusters, but you can set this second min neighbors parameter to control the extra bookkeeping you have to do to maintain these singleton clusters. Okay. Fine. And then, the core primitive here as it's operating is to find me all the neighbors within epsilon, find me all the neighbors within epsilon, find me all the neighbors within epsilon. And so this operation is amenable to spatial indexing techniques, which can be implemented in log n, so that every lookup requires only a logarithmic number of steps. Remember, as we talked about in the scalability lecture. And so the overall runtime of this is n log n. All right. So some disadvantages here is that it's sensitive to Euclidean distance measure problems. And if you remember a few lectures ago, I made a point to say that whenever you see Euclidean distance, you should be thinking about there's one big major problem with it, which is the curse of dimensionality, right? So as you get a very, very large number of dimensions, Euclidean distance starts to become somewhat meaningless. It starts to get bigger and bigger and bigger, and the data set starts to get sparser and sparser and sparser. The space that it's embedded in is very, very sparse. But k-means also has this problem because it also tends to rely on Euclidean distance. And you actually can define other distance measures and adapt k-means and Dbscan both to use them. Okay. And then another problem is that you're kind of making this implicit assumption that the density that defines a cluster is constant throughout the data set. And so this is related to this concept of heteroscedasticity that we talked about that may have seemed a little unusual at the time, but it comes up in various guises in different contexts. So I want to make sure that I mentioned it. So for example, this plot is actually the same one that we generated to make the point about heteroscedasticity in the statistics segments. But what I've done is just cut out some portions of the data here and here. And so now it looks to our eyes like there ought to be 3 clusters here, right? One here, and one here. But Dbscan, given its sensitivity to this epsilon number, do you define epsilon such that this cluster is easy to detect, you know, a very small epsilon about this kind of distance, or do you find it a slightly bigger epsilon so that you can capture these kinds of clusters? And if you're not careful, I suppose here I've actually doctored this one where it's probably okay to use the bigger one, but if you're not careful, you'll you know, the density region here may be on par with the distance between these 2 clusters here, in which case with a small change to epsilon, you might all of a sudden put the whole data set into one cluster. Okay, and so adaptive epsilons, depending on which region you're in, might be something you could think about. All right. And just like with k-means, you can think about how to parallelize Dbscan, and the only trick I wanted to point out here is that you need to worry about this halo region around each cluster, or rather around each segment. So here we divide up the space into, say, 4 different processors, and each processor is going to be responsible for that space. And in the middle, internal to this processor, you can run Dbscan as usual. But when you get close to the boundary of the region handled by this processor, you need to do some careful bookkeeping. Okay, and so all the ones that are within this boundary region need to be sent to this other processor for comparison to see whether you need to relabel C4 and C6 as part of the same cluster, whether those 2 clusters are connected by a distance of epsilon or they're not. And so they'll independently find all their clusters, but then you'll merge some clusters when you combine. And you can actually express this in terms of a sequence of MapReduce jobs, which I won't go into the details of, but there's some work done by a student here a few years ago to describe and analyze the algorithm here. Okay. So finally, I just want to wrap up with this great picture from the scikit-learn Python library website, which talks about the differences between various clustering algorithms. And we've only talked about 2 of these. We talked about k-means and we talked about Dbscan. And mini-batch k-means is a online version of k-means that uses batch at a time to compute centroids. But you can see some of the strengths and weaknesses here. K-means actually doesn't do that great in any one of these admittedly tricky challenge problems, where here you would probably think that you want this internal circle to be a cluster and this outer circle to be a second cluster, and k-means doesn't quite get that right depending on where you have the starting condition. Meanwhile, these 2 clusters kind of overlap in space as well. And here, if you have a bad starting condition in between these 2 clusters, you might put them all in the same cluster. Or really anything, anytime the starting condition is up here and say down here, this one will sort of gravitate towards this cluster and this one will sort of gravitate towards this cluster and end up in the middle, and so on. Meanwhile, in Dbscan, this hop from this cluster to this cluster is greater than epsilon, and so you'll do what seems to be the correct thing, which is put the inner circle in one cluster and the outer circle in another. Similarly here, the distance between these clusters is enough where Dbscan figures it out. And similarly here. And for the noisy case, Dbscan puts all of these points all in the same cluster, which, you know, to our eyes, that's probably the right thing to do. Okay. So I think the takeaway here is that at least in these 4 challenge problems, Dbscan does the right thing in every case. And so it's a good one to be familiar with.